Hey there, it's Jason Gorman from Codemanship with the second version of a video about modular design principles in JavaScript. In the first version of this video, I used an example that was in the sort of functional programming style, which I know is very popular with a lot of JS developers. But for completeness, I thought I'd record it again, but this time do it in an object-oriented style for those of you who prefer to work in that way as well. The principles, of course, are still pretty much exactly the same. It's just the syntax that's different. So for completeness, if you're an OO JavaScript programmer, go look at the FP style one. And if you're an FP style one, then highly recommend you watch this one, which of course you are, otherwise you wouldn't be hearing this. So a modular design. Talked in a previous video about the principles of simple design, that code should work, it should be easy to understand, it should be free of duplication, unless that makes it harder to understand. And very importantly, it must be the simplest thing we could do to pass our tests. But we can tick all of those boxes and still have some problems with our design, and that's what we're going to be talking about in this video. So what are the principles of modular design? Well, the first principle, very importantly, is that each module should only do one job or have one reason to change. Why? Well, I can think of two reasons for that. First of all, let's imagine we have a module that does A, B, C, and D, and we need to make a change to the C part of that module. The danger there is we're also risking breaking other code as we edit that module, other code in that module that's got nothing to do with the logic that we're changing. On top of which we may be breaking the clients, and the more responsibilities a class has or a module has, likely the more clients it's serving, we also risk the possibility of breaking the clients that are using that module as well. So for that reason, we would look to separate modules out so that we can change each individual piece of work on its own and limit the impact of that change. But more importantly, when our modules only do one job, well, let's think about modular hi-fi. So let's stop thinking about code for a little while. So a modular hi-fi versus an integrated hi-fi. So I have an integrated JVC hi-fi. I like it very much. But I only get the JVC turntable with the JVC CD player, with the JVC radio, with the JVC amplifier going through JVC speakers, and those are the choices. So basically I get one choice as to how those components can be composed or combined into a hi-fi system. With a modular hi-fi, I could have a Sony turntable with a Yamaha CD player, with a Denon amplifier, and so on and so forth. So I get far more choices about how my system, my hi-fi system, can be configured. And that's what I call composability. And when we create systems out of modules, each of which is only doing one specific piece of work or one specific job, we get a system that is far more composable. We get far more choice about how the modules can be combined or composed together to do new things. And one of the best examples of that in software is Unix Pipes. So Unix Pipes essentially are chains of programs, each of which does one specific job, like reversing a string or converting a string to uppercase or lowercase and so on. And we can chain these individual programs that each do one job together to do very sophisticated things to strings that would be very difficult to do if it's basically one big program that does all of those things in a specific hard-coded order, a bit like our integrated hi-fi. So it's very important that modules only do one job. And to get proper separation of concerns in a system, it's vital that modules only do one job. As much as possible, modules should hide their inner working. So the details of how they do what they do, how they do their job, should be hidden from the client. The less the client knows, the better, because then there's less chance that if we change how our module works, we'll have to change the client code as well. So the less it knows, the better. Now, the style of design that we often talk about these days is called tell, don't ask. So it's very fashionable in enterprise or business kind of applications or database applications to have data classes or entities or whatever you want to call them, objects that have data. They have fields, for example. And then we have other objects that do calculations or do work with that data. In order to do that work, they have to ask for all the data from these objects that are holding the data. And that creates massive amounts of low-level coupling. If those data schemas change in some way, we're having to rewrite a lot of client logic. Much better to put the work where the data is, to encapsulate all that into a single module hidden behind a simple interface that exposes the smallest surface area possible, basically, for the client to use. For example, maybe just a single method on an object, and all of the internal details about how that method works, the data that it uses, for example, or any helper methods that it might use, or any other classes that it might talk to in order to do its job, that's all hidden from the client. The client does not need to know. And then we get true separation of concerns because we've made it somebody else's problem. That's a better way of describing separation of concerns. How do we calculate the area of a carpet? Well, that's somebody else's problem. How do we calculate the mortgage repayments? That's somebody else's problem. Where do we get the data from? That is somebody else's problem. We don't need to know. And therefore, when those details change, we're not affected. We don't have to rewrite our own code. So modules should do one job. They should, there's the E word coming. They should encapsulate their inner details, their inner workings as much as possible, so clients know as little as possible about how the work is done. And they should have swappable dependencies. So modules should be swappable. We should be able to plug them in or wire them in, usually by a mechanism called dependency injection. So the client doesn't actually know which implementation of that module it's talking to. It only knows the interface. It only knows what it looks like from the outside. And of course, in JavaScript, this is very easy to do. And that is very, very important because that swappability allows us to create flex points, if you like, in the design where, for example, we could swap an Oracle database with a SQL Server database without having to rewrite our core logic. Because if that is neatly encapsulated behind a simple interface that is swappable by dependency injection, then we can have different implementations of data access that the business logic doesn't need to know about. It's somebody else's problem. So those often I look as being sort of the three legs of the tripod of modular design. Each module doing one job, each module hiding, encapsulating its inner workings, and each module being swappable or having swappable dependencies, usually by dependency injection. And that gives us enormous amounts of flexibility in our design, true composability and true separation of concerns, which, as we'll see, is useful for all kinds of things. There's one final principle that's kind of language specific, and I think for completeness, I'm going to mention it here. So if you're working in a statically typed language like C# or C++, you do need to think about what interfaces, what's on the interfaces that your classes are exposing. Because when a client binds to an interface or binds to a type, in static languages, usually what happens is they're binding to all of the members of that. They're binding to a version of that interface. And if anything on that interface changes, that client code needs to be recompiled, retested, and redeployed, even if it's features that that client is not using. So we would say, okay, well, in that case, you need to expose client-specific interfaces. So look at what methods a client is calling, for example, on a class, and extract a Java interface or a C# interface or a C++ interface just for that client's use. So that client is only binding to an interface that contains members it needs to see and is not affected by changes to features it's not using. Now, this, of course, in JavaScript and languages like JavaScript, dynamic languages, it doesn't really matter. It doesn't really work like that because in dynamic languages, we bind dynamically at runtime to the features we use. So because of that language feature, it doesn't matter what other features an interface have because we're not actually binding to them. Having said that, there is a kind of a flip side to this final principle of client-specific interfaces, which also comes at it from the client's point of view, but is more about what the client knows that they don't need to know. And we'll see an example of that later. So there you go, 4 principles of modular design. Each module should do one job. Modules should encapsulate or hide their inner workings, especially their data. They should have swappable dependencies, so we'll be able to swap one database with another database or one mortgage calculator with another mortgage calculator and not have to rewrite the client code. And this is usually done by dependency injection. And finally, we need to think about what each module knows about other parts of the system, and in particular, whether it's depending on things that it's not actually using. And we'll see an example of that later. Okay, let's do an example. Oops. Let's do a little example here. So I've got some code here that calculates quotes for fitted carpets. So we give it the length and the width of the room that we want the carpet in. and we give it some information about pricing, the price per square meter of the carpet, on whether or not we should round up the area of the carpet when we price it. So for example, if that's true, then an area of, if the room area is 50.5 square meters, we would round up the pricing to 51 square meters, basically. It's a very simple piece of logic. Let's just check first of all that it works. Always a good idea before you start refactoring code. So our tests are passing, so that ticks the first box of simple design. It works. Is this code easy to understand? I think it is. Is there any duplication here? I don't think there is. And is this the simplest thing I could have done to pass the test? Probably. So this ticks all the boxes of simple design, but that's not to say that this design doesn't have potential problems. So let's think now about modular design. First of all, does this module do only one job? Does it only have one reason to change? Can I imagine wanting to change part of this code, but not the rest of it? Change this code, bits of this code at different times for different reasons. Well, for example, maybe we want to change how the area of a room is calculated without changing how we price the carpet for that area of room. So arguably, these should be in separate modules. One module that calculates the area of the room, and another module that calculates the price of the carpet based on that area. So let's split these out. First of all, let's put them in their own methods. So let's just call that area. And of course, as soon as I do that refactoring, I retest the software. Very important. Okay, and let's do a similar thing for pricing. So let's put that in its own method. Call that price. And again, immediately retest the software, make sure that we haven't broken anything. Very important. Okay, and I can probably inline that. We don't really need a local variable anymore. Lovely jubbly. Right. Okay, now we've got them in their own methods, but they're still in the same module, and I want them in separate modules so that I can change the way the area works, for example, without having to touch carpet quote. So what I'm going to do is I'm going to do a refactoring called extract class. Now, as much as possible, I try to use automated refactorings, which is why I'm a big fan of the JetBrains tools, because if you're a JavaScript programmer, WebStorm has a lot of refactorings it can do automatically. But one of the refactorings it can't do automatically is extracting a class. Just a note about dynamic languages, by the way. If you're into refactoring, you're probably aware of the fact that there are certain refactorings that require type information at sort of compile time. And because we don't have that, they can't really be automated, or not easily anyway. And one of them is extracting a class. Now, to extract a class, what we're going to do is we're going to declare a class that's going to have an area method. Let's call that class room. And I'm just going to, as a first step, cut and paste, i.e. move this stateless instance method, and then replace where we're calling it on carpet quote, on that instance of carpet quote, we're actually going to replace that with a new instance of room. So that's a single refactoring, extract class. Nice and easy, and it still works. It's very important, even if you're refactoring by hand, to do one refactoring at a time, extract class, move class, etc., and then rerun the test. So be very, very disciplined. Okay, now room, I want this, again, it's still in the same module, it's still in the same source file, so this really belongs in its own file. So I'm going to move this. Again, this is not one that they've managed to automate, so I'm going to do this one manually. So I'm going to cut the code for the class, and I'm going to replace it with an import. Imagine we have a module called room. Let's declare that. Paste our class in, and then export that. Nice and easy. And yeah, that looks good. So let's rerun our test. So that's move a class to another file. Back to carpet quote, looking good. Right, okay, so far so good. Let's do a similar thing with price. So let's imagine, what is this the price of? Well, it's the price of a carpet. Let's cut and paste, i.e. move this price instance method. Much easier to do it now because the method is stateless. I've kept it stateless for now. And again, we need to change the target of this invocation to a new carpet. So that's a single extract class there. And now I want to move carpet into its own module. So each module now is only doing one job. So let's cut that. And let's import from a new file that we're going to create, a new module called carpet. Paste it in. There we go. We should be able to rerun our tests. So now we have 3 modules, each of which is doing one job. Room calculates the area of the room that we're going to fit the carpet in. Carpet calculates the price of that carpet depending on whether or not we're rounding up to the nearest square meter and what the price per square meter is. And carpet quote now really essentially is just combining those two things. It's what you might call a composed class in the sense that what it does is just coordinates the work between carpet and room. But so we're ticking the first box now of modular design. Each module is doing one job. But arguably quote and carpet quote know too much about how the area is calculated. It knows, for example, that this is a rectangular room. It has a length and a width. So the next thing I'm going to do is I'm going to encapsulate the data that's involved in doing these calculations so that carpet quote doesn't need to know what data is involved in calculating the area, and it doesn't need to know what data is involved in calculating the price. So in order to do this, what I'm going to do, I'll start at the client end. I'm in the habit of starting at the client end. So we want our area method ultimately to have no parameters. So we're going to swap that with a constructor for room. Let's see if it will do that for me. Okay. And that looks good. And let's see if it will create fields for me automatically. Length and width, please. Okay, that's looking good. And then what I'm going to do here is use those instead because we got rid of those. I've done that in one step there. If we go back to carpet quote, so now the area method doesn't involve any data. It's just there's no parameters at all. Okay, should be able to rerun our test now. Fingers crossed. Lovely, right. Now that I've done that, as you can see, carpet quote still knows about length and width. How can we make it so that it doesn't need to know that? Well, we could pass the room in as a parameter. So let's introduce a parameter for room, like so. And you'll see what it's done there with that refactoring is it's added. So essentially it's taken that expression and passed it in as the parameter value when it added that new parameter. Now, what it hasn't done is it hasn't actually added the necessary import. So my code is currently broken. So I need to very quickly add the import. If anyone from JetBrains is watching, that would be really nice if you could add that as well to complete the refactoring. Okay, so now our code should be back to working. Let's rerun our tests. And no, it doesn't like that. What have I done here? That should work. Was it because I didn't save any of the files? No. I've got a feeling I know what's happened here. No. Prompts room require... paths. Oh, JavaScript. File paths. There you go. That's the correct path. This is why we test. In case you were wondering, it's also why we pair program, so someone can spot those things. Right, we're back in the room. Lovely. Now that we've done that, carpet quote, the quote method here no longer needs to know the length and the width. So what we can do is we can remove those from the list of parameters, change the method signature there. And what WebStorm will do very cleverly was it'll automatically remove wherever quote is called, it'll remove those parameter values as well. So that should all work. There we go. Lovely. So we're definitely getting somewhere now. It doesn't know anything about how the area of the room is calculated anymore. And we need to repeat this process for carpet. So what I'm going to do is I'm going to add those to a similar kind of thing. So we're just passing in the area of the room now. And let's add those to the constructor. And happy with those names. And now let's initialize some fields. There we go. And now let's use the fields instead of those parameters that are no longer being passed in. I can get rid of those parameters. So a bit of a jump there, a little bit of a jump. No, room area definitely is a parameter there. Okay, we go. And that's all working as well. So that is now neatly encapsulated, and we can do a similar kind of thing that we did with the room. We can pass in this object as a parameter, like so. And again, I'm going to have to go back and fix the test code, because that's not being automatically imported. Remember that it's one up in the folder structure JSON. Okay, now we should be able to rerun our test. Lovely. So back to carpet quote. So again, we don't need to pass in those individual pieces of information. We can remove those from the signature of the quote method there. And as you'll see, carpet quote no longer knows about the dimensions of the room. It no longer knows about price per square meter and whether or not we have to round up or any of that details. We've made all of that somebody else's problem. That's carpet's problem, or that's room's problem. Carpet quote does not need to know. So if, for example, we were to change the dimensions of a room, let's say a circular room has a radius instead of a length and a width, we don't have to rewrite any of carpet quote's code. As the client, it doesn't need to know. And that's the benefit of having that kind of encapsulation. You get proper separation of concerns. But we have achieved something else here, kind of by accident, really, because we're passing room and carpet in. What we've essentially got here is dependency injection. Room and carpet are being injected into the quote method of carpet quote. And that allows us to replace implementations of room and carpet with different implementations that work differently without having to rewrite carpet quote. So we've, as a side effect of encapsulating, of hiding the data here, what I've done is I've also made room and carpet swappable by dependency injection. So we could, for example, inject a circular room or an L-shaped room, and carpet quote would be not affected. And also, let's consider the relationship between swappable dependencies, between modularity and how unit testable code is. Let's say, for example, that this was involved in external dependency. This connects to some web service, and we say, well, we don't want to do that. So what we're going to do instead is we're going to stub it. Because room is being passed in from the tests, that's very easy to do. So let's imagine we have a stub room, and this just has to look from the outside like whatever. Let's take a look at what is carpet quote expecting. It's expecting an object with a member on it called area that takes no parameters, and if price is going to work, it has to be a number. So that's kind of the contract, if you like, that that carpet quote is expecting from whatever is pretending to be room. So we just come up with something that looks like that. Our stub room, it's an object with a member called area that is a function that takes no parameters and returns a number. In this case, a hard-coded test number of 150 square meters. So now it's not using room anymore, it's just using our version of room, this new implementation. But when I rerun my tests, they still pass, because as far as carpet quote is concerned, that's a room and it's got an area. So that swappability is very, very useful, not just architecturally, but in terms of writing fast-running tests as well, writing good unit tests. So modularity is very important for writing good unit tests. And if you think about it, if you start by writing the tests first, if you're doing test-driven development, and you're using stubs and mocks and dummies, you're going to probably end up with a design that is more modular, more effectively modular. So TDD has a tendency to drive more modular designs. And these things, it's a little bit chicken and egg because more modular designs are easier to unit test. And when we do the video on legacy code, you'll see how that is usually the biggest barrier to writing fast-running unit tests for our legacy code, is those external dependencies or that lack of modularity, that lack of clean separation of concerns. So it's very, very useful. And from a design point of view, very, very powerful. So there you go. That's modular design principles for object-oriented JavaScript. I recommend, if you've just watched this video and you're a JavaScript programmer, go back and look at the previous version that does it in a sort of functional programming style. Older Java developers may remember, of course, that objects in older versions, before classes were introduced to the language, the way that objects were created in JavaScript essentially was functional programming. So I've used a mechanism in that first video called closures to encapsulate data. And in JavaScript, closures, as they do in many languages, behave a lot like objects, So it's really just the syntax that's different. In terms of modularity, functional programming versus object-oriented programming, it's a non-argument. When people say, well, you can do more modular code one way or the other, it's simple, palpable nonsense. They're both just as modular, and it's just as easy to achieve proper separation of concerns doing it in either style. Now, there's one final thing we should look at. If you remember from the PowerPoint slide, there were 4 principles of modular design, and the 4th one I said was kind of language specific. So in, for example, Java and C# and C++, we need to think about what features are actually being exposed on an interface so the client is not made dependent upon features that they're not using from a class. So interfaces need to be client specific. And that doesn't really apply in dynamic languages like JavaScript, for example. But that doesn't mean to say that we shouldn't be thinking about whether or not our modules are depending on things that they're not using. So if we take a look at our carpet quote module now, you'll see that it has 2 unused imports. So it's importing room from the room module and carpet from the carpet module. Now, what happens if I make some kind of change? Let's say, for example, we decide to move room to a different folder. And then I try to run my code. Carpet quote is now broken. I've broken carpet quote by changing something it wasn't even using. So it's super, super important. Let's just move that back. It's super important that our modules don't depend on things that they're not using. So that's kind of like the flip side of client-specific interfaces. That in dynamic languages and in non-dynamic languages, modules should not depend on things they're not using. So let's get rid of those unused imports. And we'll see now, having done that, rerun our tests, of course, having done that, carpet quote now has no direct implementation dependencies. The objects that it talks to, it's able to talk to them only because of dependency injection. So it doesn't know what the implementations are. And carpet and room similarly have no direct implementation dependencies. If we take a look at our test code there, you will see that all of the implementation dependencies are now contained in the client code, in this case, the test code. So our call stack, if you like, is constructed from the outside, a bit like Russian dolls. So one object is passed into an object that uses it, which is passed into an object that uses that, which is passed into an object that uses that. And our call stack, the actual flow of control of method calls, is determined dynamically from the outside by the client. And we call this inversion of control. That's the technical term for it. And it's a very powerful way of composing systems out of modules using dependency injection. So the actual flow of method calls or function calls, if you're doing it NFP style, is determined ultimately by the client, and only the client knows which implementations are actually being used. So for example, here I was able to swap an instance of room with another object that just returns a hard-coded area, a stub object here. So inversion of control is the basis of a lot of really, really good modular design. And a good sign that your code is genuinely modular is that good modular code tends to wear its dependencies on the outside, like this code is doing here. So there you go. That's modular design in JavaScript in the OO style. If you're a JavaScript programmer and you're curious, go take a look at the previous version of this video and see how this works in a functional style. And in upcoming videos, particularly when we talk about the testing pyramid and legacy code, we will talk about why modularity and separation of concerns is so very, very important in order to achieve proper continuous delivery.